Hello, today I'll be discussing Lab 3, titled Magnetic Field of a Bar Magnet. The purpose of this experiment is to observe, model, and analyze the properties of a magnetic field produced by a bar magnet using the fundamental principle of Biot-Savart's law. Specifically, we use the observed effect that distance has on the magnetic field to find the dipole moment and produce a model to visualize the bar magnet's magnetic field at various locations. Derived from Biot-Savart's law, we get this general equation for finding magnetic fields. And given the condition that the position vector r is much greater than s, the separation distance between the magnetic poles, we get the approximations for the magnitude of the magnetic field by dipoles on axis and perpendicular, given by these expressions, where on axis is twice as large in magnitude as perpendicular to the axis. Before I get into the exact apparatus, it's important to note that for our observations, we're trying to find the relationship between the magnitude of the bar magnet's magnetic field and this r to the n value, where I can find out that k is just given by this approximation based on how I set up my apparatus. So to set up my apparatus, I first initially found where the net magnetic field without the magnet present was 0 in the x-axis, which indicated my phone was aligned with the Earth's magnetic north to south axis. The magnet was then placed with the dipole aligned with the east to west axis, as seen here, so its on-axis magnetic field was perpendicular to the Earth's magnetic field. And we do this so my magnetic meter will only have the bar magnet's magnetic field represented in the x calculation for the magnetic field. Now moving past the setup, I recorded the magnitude of the magnetic field in the x at various distances to demonstrate the relationship between r and the magnetic field base, which is presented in this graph here, where this formula in slope-intercept form is given by this expression here. So we can use this expression to first find this n value, which I got to be approximately -3, which when we look at this formula right here is exactly what we expect. R to the cubed in the denominator. We can then rearrange this formula for k to get our value for the magnetic dipole mu, which for my case was 1.3. One last thing before moving on to the model, I also got a value for the magnetic field off axis at an angle 45 degrees, which you can see from this apparatus setup. Here I ensured to account for Earth's magnetic field at the location first, which is how I was able to get these corrected values. One last thing to note is this value for the z. So you notice that these values are like 2 magnitudes behind all the other ones. So these can be assumed to be approximately 0. And we do that because when we're getting the magnetic field, we're really only working with the x and y axis. So the z axis shouldn't be changed. Alright. For the model, I used the observed mu data and also this equation for finding the general magnetic field. Those are very important for the model. So first we created the magnet centered at the origin. We inputted our calculated magnetic dipole moment from our observed data. I have a function for the magnetic field using that formula I described earlier. Here it's important to note what our R is. So R is usually calculated by absorbed minus source. Here our source is the origin, is at the origin, so that's why R is actually just going to be our absorbed positions, where I have 2 absorbed positions on axis and 2 perpendicular to fully just encapsulate the visualization of the magnetic field. I'll have a 7th arrow as well for the 45 degree off axis. Right, so these orange arrows on axis are about twice as large as our perpendicular ones, the cyan arrows, which is as expected. Even smaller is our 45 degree magenta colored arrow. But this visualization is pretty much exactly what we expect. Here I also calculated the magnitude for the magenta colored arrow, as we can compare that to our observed one. When compared, I got a percent error equal to 26.6% for these. Now, to close things out, let's consider these two what-if questions. First, what if we didn't compensate for magnetic north initially? If we didn't compensate for magnetic north, our observed data would include the magnetic field by the Earth, which would skew all our preceding calculations. Thus, our percent error would be through the roof. Second, what if instead of using a single magnet, we use two identical magnets stuck together end to end? Assuming that the distance r is held constant, the magnitude of the magnetic field would double as the value for mu, which accounts for the separation distance between the poles, would have also doubled. And with that, thank you for watching. I hope you all have a great day.